Material decay is proportional to the amount of material left. After 35 years, half of the original material remains. After 100 years, how much material expressed as a percentage is left? Now, it asks for the amount of material left after 100 years. But the problem with that is that we're only given the relationship between the decay rate, and the amount of material. The decay rate we can express as as a derivative, so dr over dt. R represents the radioactive material left. Usually decay is radioactivity. So this is the radioactive material. And this is unit time. This is, if this was a graph, dr over dt would be the slope or the rate of decay in each point. So now it said here that uh the rate of decay is proportional to the amount of material left. So that would be K times R. K is the constant of proportionality, and R is the amount of material. So there we go. Now that we have this differential equation, we can solve this using the established methods we discussed earlier. So this is separable. So we can solve it used by dividing both sides by r and then leaving k on the other side. Now integrate both sides with respect to t. On one side we get ln of r, and on the other side we get kt, and then don't forget plus c. Now we can put plus c here, but it would be subtracting a constant to constant if it goes to the other side, so we can just have one constant on one side. Then we can raise e to both sides. E and ln will cancel out. We get r there. And e and kt plus c, I guess, will become kt plus c. Now, e to the kt plus c. This can be expressed as e to the k e times e to the c due to the law of exponents. E to the c, e to the power of a constant is still a constant, so we can put that as the new constant. So c times e to the kt. So let me write that again. R is equals to uh, C e to the k times t. Now, since there's only t in here, no r, we can say that r is a function of t. As t changes, r changes along with it. So that's the logic with that. Now, it says here, after 35 years, at 35 years, only half the amount is left. So that means at the start, there was a full amount. So let's say this is 50%. So it must mean that then t at 0 years, at the initial time, there was 100% of the material. So we will be using 100 as the initial amount of material, and 50 as the amount of material after 35 years. So we know r of 0 is 100. Plugging it in here, we get c times e to the k times 0 is just going to be 0, regardless of what k will be. So e to the 0 is 1, so 1 times c is c, so c is 100. So let's rewrite r of t. 100 e to the k t. Now here's where you're going to bust your calculators out. So r of 35, which we know is 50, is also 100 times e to the k times 35 years. So we need to isolate k's. We need to find k. So divide both sides by 100. So we get 50 over 100. Then this is equals to e to the k times 35. To remove the e, so we get k times 35 here. We can take the natural logarithm of both sides. Ln of e, the ln and e would cancel each other out, leaving us with 35k on one side and ln of 1/2 on the other. And then Now, in order to have we need to divide by 35. So 1 over 35 times ln of 1 half. Let us input that into our calculator. I will zoom in so you can see. There. So this is my calculator. I'll just input 1 over 35 times ln of 1 over 2. Okay, so this is what I input in, and what I get is a negative 0.01980 dot dot dot. And it's negative, we know that because it decays. So as time goes on, there would be less material. So this being negative makes sense. So let's go back to the first one. So we know K is, I'm going to store this just for clicks. You can store that. We know K is negative 0.01980 dot. And then the unit for this, since the 35 means 35 years, we need to cancel that out. So we get the unit inverse years. So that's fun, but that's not really useful. It's just formalities, you know? So now let's put the complete function r of t. This is then equal to 100, that's the C, e to the negative 0.19804 inverse years times t in years. All right. If t is in years, the years here, they cancel each other out. That's very good. So now we use this in order to find the amount of material left after 100 years. So R of 100, that's what we're trying to find. 100 times e to the negative 0.19804 inverse years times 100 years. This and that would cancel each other out, leaving us with no units at the top of the exponent, which is good. So we're going to calculate it again. 100 times e to the negative, uh, no, I'm going to put my stored value, times 100, we get 13.80% of the material left over. That seems about right. R of 100 then equals 13.80% of the material left. Let me check. Yes. So that's going to be our answer. So that's going to be an answer. I should note that there's an error in here. 0.0. Right. Sorry about that. And 13.80% of the material is left. That makes sense. This is 100 and 35 times 3 is 105 years, right? So if we expect in 35 years we will have 50%, if you double that, we will have 25%. So 70 years we will have so in 35 years we have 50%, in 70 years we have 25%, and in 105 years, which is 3 times 105, we will have around 12.5% of the material left. And this is about right. It's above 12.5%. So our answer makes sense.